This is a video on the mathematics of gambling, specifically a derivation of the Kelly formula. First, some basics. Sports betting usually is done in odds against. 2-to-1 odds, for example, means 2-to-1 against, and that's two ways the event does not happen and one way it does. It also means for every $1 bet, every $1 bet would actually pay $3 if you win that bet. That is, the $2 profit and the $1 that was actually bet are returned as winnings. And finally, it also means the odds imply a probability of a particular event as one way it could happen out of 1 plus 2 total possibilities. In other words, 1 over 3 or 33%. Now, moneyline odds are a way in which odds are often stated in sports betting, particularly in the United States. Negative means a favorite, positive means an underdog. For example, a money line of minus 120 means the odds are 100 to 120 against. That's equivalent to 0.83 approximately to 1 against. And that means every $1 bet would return $1.83 if that bet wins. And further, the odds can be interpreted as probability as follows. So you have one way it could happen out of 1 plus 0.83 approximately total possibilities. That's 1 over 1.83, which is about 0.54, meaning a 54% chance. So a minus 120 money line really implies a 54% probability. Now, as another example, a money line of 150, a positive 150, that translates to odds against as 150 to 100. One could look at it as every $100 bet would pay 150 in winnings in addition to the $100 return. So the profit would be 150 for every $100 bet. That's equivalent to 1.5 to 1, means every dollar bet would return $2.50 if that bet wins. And further, those odds can be interpreted as probability as follows. One possibility of the event winning out of 1 plus 1.5 total possibilities, that's 1 over 2.5, it's about 40%. You can see this is an underdog, an unlikely event, only a 40% chance. That corresponds to a money line of positive 150. Now, the point spread was created by Charles McNeil in the 1940s. McNeil lived from 1903 to 1981. McNeil was a high school math teacher, but also worked in the as a stock market analyst and eventually a bookmaker. And it's interesting to know that John F. Kennedy was one of McNeil's students. So an example with the point spread, let's say you have the Cowboys plus 3.5 at minus 110, and the Eagles minus 3.5 at minus 110. So that 3.5, that 3.5 is what's called the spread, and then in the parentheses, that's the money line odds on that spread. So you bet the plus if you think the Cowboys will win outright or will lose by less than 3.5 points, 3 or less points. And you bet the minus if you think the Eagles will win by more than 3.5. In other words, they'll win by 4 or more points. So this is John Larry Kelly Jr. He lived from 1923 to 1965. And he developed what's called the Kelly criterion. It's a formula to proportion bets based on a disparity between given odds and what the true odds are. And Kelly was a research scientist at Bell Labs. This is a 1956 paper introduction that introduces the Kelly formula. So in that paper, you find this formula. It's called the Kelly formula. X is the fraction of the gambler's bankroll that's going to be wagered on a particular bet. P is the true probability of a particular event. Of course, that may be difficult to determine, but P represents that true probability. Q is the probability the event will not occur, and so always Q is just 1 minus P. B is the given odds on the event, whatever the bookmaker sets as the odds. And so that would be something you might see 3 to 1 odds, 2 to 1 odds, or something like 0.83 to 1. Depending on what the money line odds are, you can translate that to find the number B. And then this formula can also be referred to as a criterion in the following sense. You only make a wager when the fraction to be wagered is greater than 0. In other words, when x is bigger than 0, it tells you that's when you make a bet and how much you bet. So Kelly found a way to maximize the rate of growth of capital when there's a difference between the true odds and the given odds. And he also translated that result into a measure of the information rate in bits per unit of time that are required to attain that maximum growth rate. Okay, where I'm going to start is with a formula that can determine how the bankroll will go up and down as you win and lose bets. So this is what I call the compounding bankroll model. And it's from this that I will then derive the Kelly formula. So A sub n here is the amount of money in dollars in the account after n bets. A sub 0 is the starting amount of money, the initial bankroll, the amount that you have when you've made 0 bets, your starting amount. N is the total number of bets, and N is equal to W plus L. So we don't know how many we're going to win or lose ahead of time, but whatever that is, that's the total number of bets when you add them together, right? W is the number of winning bets, L is the number of losing bets. Now X will be the fraction of the bankroll that is wagered at each bet, and B represents the odds that are given in a particular event or wager. So they would be generally written as odds of B to 1, but we're using the value B when it's written in that form, B to 1. Right, so we are setting up a formula that will determine the future amount based on however many wins we actually may incur and how many losses. We don't know that ahead of time, and we're going to use this to model what that future account balance would be after a series of bets. So first I want to just explain that bankroll model, and here's a very simple example. Suppose that you had $100 available for wagering. That was your initial bankroll. A sub 0 is $100. You look at a particular event, and the odds are given as 2 to 1. So here the B value is 2. And let's say I'm going to bet 10% of my money, which in this case would be $10. So we have A sub n from that bankroll formula, now plugging in the values. A sub 0, that was my $100. That's going to go here. That's my starting amount. This is the B value. Those are the odds that are given on the particular event. This 0.1 is what I'm actually wagering as a percentage of my bankroll, and then it occurs here again. This 1 minus 0.10 is 1 minus X in that bankroll model. W is the number of wins that I will incur, and then L is the number of losses that I will incur over a sequence of n bets. So these expressions simplify to 1.2 and 0.9, and so you can see that this means that if I'm betting 10% of the bankroll at 2 to 1 odds, with each win my balance would increase by 20% because I'm betting 10% at 2 to 1 odds. So each time I win on that 10% bet, I get a 20% increase in my bankroll. However, of course, if I am betting 10% of my bankroll and I lose, then I'm going to lose 10% of my bankroll, and so for every loss I will have 90% of the previous balance. And the balance is therefore, of course, dropping 10% each time I lose on those 10% bets. Suppose we had, as a specific example, suppose we had 2 wins and 2 losses. What happens to the future bankroll? So 2 wins, I'm going to do 1.2 to the power 2 and 0.9 to the power 2. So we end up with a balance after 4 bets of $116.64. So that's about a 17% return on that investment. Pretty good. We were betting 2 to 1, so it's not likely that you would win 2 and lose 2 if the odds really were 2 to 1. But there it is. That's a particular example of the compounding bankroll. Okay, just as another sort of extreme example to just sort of explain the basic starting formula here, suppose we had $100 and we were given even odds, that is 1 to 1, B is equal to 1 when you have even odds, so it really implies a 50-50 probability. Suppose that we bet everything. 100% of the bankroll is wagered on a game that is 50-50. So in that scenario, my bankroll formula is my starting amount, $100. I have a 1 plus 1 because the B value here is 1 for the even odds. And if I bet 100%, I have X equal to 1. And then I have 1 minus 1 in this other factor. And so it really depends on how many wins and how many losses I have, of course, to determine my final bankroll. Imagine if you were betting on an event that was 50-50 and you bet the entire bankroll at even odds, then every time you win you double your bankroll. So my initial bankroll would be multiplied by 2 with every single win. But of course, if I'm wagering 100%, a single loss, as soon as this factor of 0 enters into the picture, the whole balance goes to 0. I would lose the whole entire thing if I lost one time when I have 100% wager. So I'm going to do a sort of technical little detail here and say that my formula is legitimate in this form if I just, for the moment, for this situation, say, well, let's just call 0 to the 0. So if you had 0 losses, this is a factor of 1. It doesn't count until the first loss comes up, and of course everything goes to 0. So for our purpose here, I'm just defining 0 to the power 0. Count that as a 1. And recognize with each win, our bankroll is doubled, but with just one loss, we'd have the bankroll go to 0, and we would be done there. So what I want to do is not bet the entire bankroll on every single bet generally, right? So what I'm looking to do is to maximize the growth rate in that bankroll, and the way that I do that is to define this expression, a sub n over a sub 0 to the power 1 over n minus 1. This is called G. It's a compounding growth rate per bet. As an example of this formula, suppose that we bet once per week for 4 weeks, and our bankroll grows from 100 to 150. That's very optimistic, but it's just an example. Suppose that a 50% return on investment, if I went from 100 to 150, that's a $50 increase with a starting amount of 100. That means I have a 50% return on investment. And what is the weekly compounded growth rate? What is the value of G under those circumstances if you go from 100 to 150 with 4 bets once a week? Well, plug all those values into that G formula up there, and you have 150 over 100 to the power 1/4 minus 1. In the end there, simplifying that, I come up with about 0.1067, about 10.6%, 10.67%. What that's saying is that if you increased 50% over 4 weeks in 4 bets, you're increasing at a rate of 10.67% per week. That's the growth rate. That's the per week and per bet growth rate. 10% every week for 4 weeks actually gives you a 50% total growth. Of course, that's happening because of the compounding. Each time it's bigger, 10% actually represents a larger amount. So 4 weeks of 10.67% growth will produce a 50% increase overall. In other words, 10.67% growth per bet over 4 bets would yield a total of 50% return on investment. A growth of 10%, let's say, gives you 110%, right? And if you get that 110% 4 times, you'll make $150. And such an outcome would occur if you were risking 27.5% of the capital at even odds, and you won 3 out of 4 bets. Right? So suppose you were given an event that had even odds, and for some reason, crazy reason, funny story how I came up with that 27.5, but that comes from the Kelly formula. So let's say you were betting 27.5% of your capital at even odds, and you won 3 and you lost 1 time. So if you're betting 27.5%, you would get 27.5% increase because you're betting even odds, so you only get what you invested back as profit plus your investment, right? So that's a 27.5% growth in the account 3 times. But then you lose that one time, so that's a 27.5% loss. That means you would have 72.5% of your balance when that loss occurs. And so you multiply all that together and you hit about $150. So that's approximately a 50% increase. It's slightly higher, about a 50% increase, and that corresponds to an average growth rate of 10.67% per bet. Doesn't really matter how often, what time schedule here. It could be 4 times in one single day, or 1 bet a month. It's per bet that you're growing at a rate of 10.67 because there were 4 bets in this scenario. Okay, so let's now go back to this bankroll model. This is the compounding bankroll model. That A sub 0 is my initial capital, W is my number of wins, L is my number of losses, B is the odds that I'm given, and X will be how much I wager based on the given odds and what I believe the true probability is, which is where I think those W and L values will fall. Right? So we seek a value of X that will maximize the per bet rate of return G. So that max value of G occurs when that fraction A sub n over A sub 0 to the 1 over n, when that's maximized. Of course, G is maximized because G is just that number minus 1. And that fraction A sub n over A sub 0 to the 1 over n, that can be rewritten. Just divide both sides of this expression by A sub 0 and you have these two factors. And it's all to the power 1 over n. Now I'm going to distribute the 1 over n, so I've got W over n and L over n here as I distribute that to power. So of course W over n is how many times you win out of the total number of bets, which means that really that's what the true probability is. If I really knew what that was, that would be very, very useful information. I don't necessarily know precisely what that is, but that's another story, and we can work on ways in which you can try to analyze the events to try to improve your estimate of the true probability. But whatever that true probability is, even if I don't know it, of course, that's the beauty of algebra. I can give it a name. I say P is the true probability. Even if I don't know the value of P, ahead of time, I'll know it after the event is done, or after a series of events are done. I can look at what the probabilities, let's say, in the past were. So Q is the number of losses over the total number of bets, and so I'm going to write this expression 1 plus B times X to the power W over N. I'm going to substitute a P in there, and right here is where I had W over N, and right here is where I had L over N. I'm going to replace that with Q, and then I'm going to use a little trick from algebra where the exponential raised to the ln function, those are inverses, they cancel each other out. So these are equivalent by properties of the exponential, by the inverse property of the exponential and logs. So, the reason for doing this is because then I don't have to deal with these powers. You see, if I take the ln function, let's say, first of all, I want to now realize that this is fine. X is going to be the fraction of the bankroll that you wager, and therefore it's not going to be over 100%. You're not going to bet more than 100% of what you have available. So X only goes up to 1. So this ln, these factors are going to stay positive. And so the ln is defined. Further, the maximum value for this exponential function, because that's what I'm trying to maximize, the maximum value of this exponential function occurs when that ln is at its maximum. So I set my function f equal to this expression, this ln. This is what I'm trying to maximize. So here's where I can use the properties of the ln, separate it into two terms, and bring the p factor down and the q factor down. So this will make it easier to solve for x than if it had been back in this original. If you write it in this form, it'll be very hard to solve for x. In this form, it'll be easier to solve for x as we go further along. So what I'm trying to do is find a maximum value for f. And when I find the maximum value for that function f, I have a maximum for that ln. When I have a maximum for that ln, I have a maximum for the exponential, which is equal to this value that when I have a maximum for that, I have a maximum for g. I have the maximum per bet rate of return. So I'm trying to find a value of x that will maximize this function f. So when I take a derivative, it looks like this. Factor of p is constant with respect to x. It's p is whatever it is. It doesn't change with x. The derivative of the ln is 1 over the argument. So I have 1 over 1 plus b times x times the derivative of the argument here with respect to x, which is the quantity b. So times b. And then the derivative of this term, just a constant q. It's at least constant with respect to x. So q stays there. Then I get the derivative of the ln, which is 1 over 1 minus x times the derivative with respect to x. This is a chain rule factor, so I get a negative 1. And then I simplify it and write it in this form. Now in calculus, when you are trying to find a max or a min, you find a critical point. You take the derivative, you set that derivative equal to 0, so that's what I'm going to do. To find a critical point, I set that derivative equal to 0, and here's where I can actually quite easily solve for x, right? Move this term over to the other side, cross multiply, and now I'm going through the process of distribute the PB factor here, bring these two factors that have x to one side, factor out the x, divide both sides by this QB plus PB factor, and I have isolated x. Now another little interesting thing that can happen in this formula is you can factor out b. When you factor out b, you have the q plus p terms, and q plus p will always be equal to 1, right? Because q is the probability of losing and p is the true probability of winning, and so those two together have to equal 1. It's the number of losses over n and the number of wins over n, which is the total number of bets over the total number of bets. So that's 1. So this formula simplifies to just p times b minus q, everything divided by b. So we found x equal to p times b minus q, everything divided by b, is a critical point of the first derivative. And further, it can be shown that the second derivative is here, negative p b squared, everything over 1 plus b quantity squared, plus the negative q over 1 minus x all squared. It can be shown that that second derivative is negative. If you think about it, the denominators are positive because of the square. And b is positive, p is positive, q is positive. All of those terms are positive, but all of the factors, I should say, are all positive, and each factor has a negative factor in front of it, so it makes the whole thing negative. And since it's negative, I know that it's concave down. The curve is concave down at the critical point, and therefore I know that there's a maximum at the critical point. And that's the crucial thing. I'm trying to find the value of x that maximizes that function f. So here's the conclusion. The maximum average per bet rate of return will occur when the fraction of the bankroll wagered is this amount. X equal to p times b minus q, everything divided by b. P is the true probability of winning again. Q is the actual true probability of losing. And b to 1 are the odds that you're given for a particular event. So you have to distinguish between the odds that you're given and what you believe the odds to really be. So the odds that you're given are b, and the true odds that you believe them to be, that's the value of p. So here it is, right? This is the Kelly formula. P times b minus q, everything divided by b. So this can be translated as this quantity p times b minus q. That's really just the expected value on a $1 bet. If you think about the actual probability of winning, and if you bet $1, you would win for every dollar bet, you would win p dollars. That would be your profit, right? And this q is your true probability of losing, and every time you lose, you would lose $1. So that's your expected value on $1 divided by b, which was the odds. So expected value on a $1 bet divided by the odds, that's the Kelly formula. And that number on top, you can actually call that the edge. And so you only bet when the edge is positive. You bet when you have an edge. You bet when you have an edge, which means you have positive expected value on a particular event. So you bet only when you have an edge, when your expected value is positive. And this formula not only tells you when you bet, but the fraction of the bankroll that you bet is this fraction, the edge divided by the odds. So how about some examples? Suppose given odds are 2 to 1, but the true probability of the event is known to be 0.5, and therefore Q is 0.5, and we have X would be 0.5. That's the true probability times 2. Those are the odds minus Q, which is 0.5. Everything divided by 2, which was the B value, which were the given odds. Right? That simplifies to 1/4. That means I'm going to bet 1/4 of whatever bankroll I have. So if I had $100, I would bet 25, or if I had $1 only, I would bet 25 cents. So starting at $100 and betting 25% of the bankroll on a series of 10 bets. Now suppose that you had that opportunity there over 10 bets, right? And if the true probability was really 0.5, if it really was exactly 0.5, you would win 5 and you would lose 5, right? So what would be the future bankroll? If you started with 100 and on the first bet you bet 25, but then of course you may go up or down. It depends on whether you win that one. You don't necessarily win all of those 10 bets. Let's anticipate that we would win 5 and we would lose 5, but we're only betting 25% of the bankroll each time. So after a series of 10 bets, with those increases and decreases in the account, in the end we have $180.20. Betting a quarter of your bankroll at 2 to 1 odds means you would get 50% increase in the bankroll, whatever it is, each time that you win. And let's say you win 5 times. And if you're betting a quarter of your bankroll, each time you lose, you would have only 75% of your bankroll remaining. And that's why there's a 0.75 here. And we would just anticipate here, suppose that we lost 5 times. Well, with those 5 wins and those 5 losses, that results in $180 final bankroll after 10 bets. So that's an 80% total return on investment, and an average rate of return here in this particular example of about 6% per bet. So if you could grow 6% on 10 bets, you would get a total of 80%, right? Because that's a 6% growth each time. Each time as it's growing, you would have a larger amount, and 6% would therefore represent a larger amount. So an average of 6% each bet over a period of 10 bets would produce an 80% growth. So my 80% total return translates to 6% per bet growth. So looking at my bankroll formula, I would have, let's say you started at $100. You see the 2 here is my given odds. X is the fraction of the bankroll between 0 and 1 that's bet. This is the function that actually what you actually can see here would be sort of what the final bankroll would be if you bet different amounts. So let's say, you know what, it's 50-50, I don't want to bet anything. So if I didn't bet anything, I would just stay at $100. But if the true probability was actually 50-50 and you had an opportunity to bet at 2 to 1 odds, that's of course why this is producing this kind of growth. It's right around here at 25%, actually right about there at 25% of the bankroll, that you can achieve the highest under those circumstances, right? The initial bankroll was 100, 2 to 1 odds, true probability of 50%, X is the fraction of the bankroll wagered, and I'm assuming 5 wins and 5 losses under those circumstances. If that were the case, what's the best amount to bet? And you can see in the graph, it looks like about 25%. In fact, I type that particular function into the calculator and find the maximum. It occurs at about 0.25 on the calculator. This is just a error in the calculator software. It's really exactly 0.25 where the maximum occurs at 180.2 for the y value. That's the maximum for that function. Well, that's nice. We found the point, if you really had 2 to 1 odds and you had a 50-50 opportunity and 10 bets, the most you could get out of that with 5 wins and 5 losses would be $180. That's just one particular scenario. Of course, the Kelly formula, what's so beautiful and fascinating about it is that we're finding the X value that will result in the maximum final balance for any possible starting balance, with any possible number of bets, with any possible given odds for any true possible, no matter what, regardless of what the true possibility of the event is. No matter, in other words, all of those quantities are all variables that you could say, well, if you knew what they were, plug those in and that's the right amount to bet under that circumstance to achieve the maximum growth rate, and therefore, of course, the maximum balance. All right, so now let's look at a second example. Consider moneyline odds on a team of minus 110. That corresponds to odds of about 0.91 to 1, which in turn corresponds to an implied probability of about 52%. Suppose the true probability of the event is in fact 55%. So that number minus 110, that's often used as the moneyline odds on a particular point spread. That implies a probability of 52%. That often is on both sides of the point spread, and therefore that 52% plus 52% goes over 100%. That 52 plus 52 makes 104. That 4% is the actual profit that the bookmaker is building into the odds that they're giving. Now, if I thought that the probability was higher than 52%, that, say, the Eagles beat the spread, if I thought the probability was 55%, just a little bit higher, then I might think I have a little tiny bit of an edge. So let's mathematically calculate exactly what that edge is, and based on what the given odds are and what I think the real probability is, and how much I have in my bankroll, how much should I actually bet on that particular event, right? So the given odds minus 110 really means 0.91 to 1. That means a 91-cent profit for every dollar bet if that bet actually wins. It implies a 52% probability that the bookmaker is setting, and let's say I think the true probability is a little higher, 55%. Maybe I've done a lot of analytics on the teams and I have some sort of inside information here that I think either inside information or just real careful analysis. So what does the Kelly formula say? 0.55 was the p-value, that's the true probability. 0.91, that's b, minus the 0.45, that's q, that's the probability that I don't win, divided by the 0.91, that's the odds. So here I could really say mathematically I've defined edge, and I have this sort of almost a little higher than a 5-cent edge here on this particular event when the odds are 0.91. So that means about 5%, 5.5% of whatever bankroll I have, I should bet 5% on this particular event, 5.5% of my bankroll to achieve sort of the maximum average rate of return. Now this is only for one particular event, but imagine I had many of these particular opportunities, then this is how much I would bet on each and every one of them. So the Kelly formula says bet 5.5% of the bankroll. Suppose you had 20 such opportunities, and if the real probability was actually 55%, let's suppose that it turned out that way, and you actually get 11 wins and therefore 9 losses. I'm thinking 11 is 55% of the 20, so I win 11 times, I lose 9 times. There's only 55% chance of winning, but if I got 11 right out of 11 right out of 20, I had 11 right, 9 wrong, the bankroll will grow after 20 bets, starting with $100, with 0.91 odds, with 5.5% risked, with 11 wins and 9 losses. Final balance $102.85. Okay, that's no windfall, but imagine extracting a steady 2 or 3% daily or weekly increase in one's bankroll from small discrepancies in valuations of the various matchups between teams. I mean, that's exactly what a stock market analyst does for stocks, looking at arbitrage opportunities. small differences in the valuations between the offering price and what the real value is, right? And that 2%, if you could get that over short periods of time, could produce a very decent return on investment. So that 2% is actually significant. I mean, it's growth, and if you get that steady growth, that's pretty neat. Suppose we really could find a 2% return each week for an entire season with an initial bankroll of A sub 0. So whatever that starting bankroll is, if you got 2% every week over 16 weeks, that's a 37% increase, 37% return on investment. Yet, let's say 20 weeks of baseball, 2% growth every week, that's a 49% total return on investment. So how about a year? Let's just say you try all the major sports throughout the year, you got that 2% every week for 52 weeks. So whatever your initial bankroll is, you could multiply that by 2.8. That's almost tripling your investment. Well, it's all really nice, but the Kelly formula is only useful if we know the true probability of the event. And that's actually, it has to be different from whatever the given odds are. So you only have an advantage here if you know the true probability and the bookmaker doesn't. We must either have an inside wire, some kind of secret information, or just a better estimate of the probabilities than what's given by the odds maker. So sometimes the odds maker may actually set odds based partly on their expectations of the betting public and not based solely on their own estimates. So they may be adjusting the odds for example, a game with Yankees and maybe the Red Sox, maybe against a smaller, less popular team. You put a little overvaluation in the home team for large markets. And so there could be some overvaluations that could lead to just small discrepancies in the given odds and what they really are. So in other words, the opportunity could arise with careful statistical analysis of the events and when the odds are just swayed also by misinformed bettors that are changing the odds maker's line because of the direction in which the popular bets are going. So how do you get at the true probability for a particular event? So this is the one of the things that you can apply sabermetrics. Sabermetrics comes from this an acronym for the Society for American Baseball Research. That's the origin of the term sabermetrics, metrics for measure, and it's all of the modern analysis of baseball, statistical analysis. One of the things that you would discover in that subject is this interesting little formula for probability of winning based on runs scored and runs allowed for an individual team. This is just the beginning. There's an incredible amount of research. I'll reference a book by Joe Peta. He says the sabermetrics, all of the baseball statistics that we're all familiar with, that's sort of like accounting. Sabermetrics is like physics. And so that really, I love that quote. And this is in the beginning of that sabermetrics, one of the formulas from that field. And then in the realm of football, there are several websites that do this kind of work. Advanced NFL Stats, Football Outsiders. Football Outsiders is the one that uses this defense adjusted value over average stat that I find really interesting. Okay, and then I'll say another further word or two here about analyzing individual matchups between teams. Right? We can analyze teams and determine their win expectancy in general against average teams. I mean, you could start with their average, their percentage of games won, and just use that as a first starting point. How many games have they won so far out of the total number of games that they've played? And you can start with that as a probability of winning, right? If they've won 6 games out of 10, you can say they have a 60% chance of winning. I don't think that's going to take you very far because it all depends on who they're going to play next. But that's what I'm talking about. That's sort of winning, the probability of winning, right? They're determining a team's probability of winning. You could begin with how many games have they won out of the total, right? So now let's consider two teams, Team A and Team B. Suppose we estimate the probability that A wins. For example, probably A wins 60%, and the probability that B wins, let's say 65%. Let's say that those represent win probabilities against some average team. Right? So that's what P A wins represents. The probability that A wins against an average team, probability of B wins against an average team. Now we'll look at what happens when A plays B, when Team A plays Team B. So if we have the probabilities that a particular team wins against average, we can estimate the probability either team wins against a specific team, against each other, as follows. Right? The probability A wins and B loses as an example. We'll just multiply the probability that A wins against an average team, multiplied by the probability that B loses against an average team, and divide that by either A wins, by the total, right? The probability A wins times probability B loses, plus probability A loses and B wins. These are sort of the total possibilities in a sense here. Either A wins or B loses, or A loses and B wins. And so I'm calculating the probability that A wins against B using probabilities that A wins against an average team and B wins against an average team. Okay, so this is the end of my video, and there are two books that I'll recommend for further reading. Trading Basis, a story about Wall Street, gambling, and baseball. Not necessarily in that order in the title there. Book by Joe Peta. And Fortune's Formula, the untold story of the scientific betting system that beat the casinos in Wall Street by William Poundstone. That goes into the history of the Kelly formula and the history of gambling on sports, and really an interesting book. And then finally, if you're in most of the U.S., it's illegal, technically illegal, to bet on sports in most of the U.S. So if you're interested in this, one thing that's an option to avoid illegal sports betting is to go onto a website such as sportsplace.com, and there you can create an account and bet with just really essentially pretend money on that account, so it's not really gambling with real money and not illegal sports betting. Okay, that's the end of the video. Thank you very much for watching. I hope it was interesting.